Hello and welcome to this question walkthrough of a moles and gases question that's a little bit applied in the way it's presented. With a bit of input, maybe we can take you through how you can tackle this type of question. So it says a nitrogen fertilizer has a composition by mass, and it gives you a percentage for each of the elements up here, and we need to use these to calculate the empirical formula. So you divide the percentage by the relative atomic mass for each element, first of all, dividing each answer from step to by the smallest, and that gives you a whole number ratio, hopefully. If you don't get a whole number ratio, you can multiply it by the lowest common multiple. So 27.1 over 23.0, 16.5 over 14, 56.4 over 16 gives you these numbers. So you find the smallest is obviously 1.178, so you divide by that through each time, and that gives us 1, 1, and 1.980. You can approximate 1.980 to 2, and that gives you NaNO2. So writing an equation for the decomposition of A, what's interesting here is it says that A decomposes into NaNO2 and oxygen gas. Now, we've already worked out the empirical formula of A to be NaNO2, so this requires us to realize that the empirical formula is actually the simplest whole number ratio, not the actual whole number ratio. So it's the molecular formula we need to try and work out, and then construct an equation using that. So, with that apparent contradiction in mind, let's just go back to the start. Compound A breaks down into NaNO2 and O2. This means we need at least 4 oxygen atoms on the left-hand side of our equation, because there's 4 obviously in the products. You need to remember that sodium is a group 1 metal, so we'll form +1 ions, and therefore you need to think about what ion goes with the sodium in compound A. So doing a little bit of a play around with balancing numbers, and remembering that there's more than one nitrate ion to choose from, we can use sodium nitrate with nitrogen in oxidation state 5 instead of sodium nitrate with the oxidation state in +4, I think it is, in NO2 minus. Just checking that. No, it's +3. So we can have nitrate 5 or nitrate 3. Now, nitrate 3 is also used to be called nitrite, so that's what nitrite comes from. So we now know what the equation is for this reaction. We want the volume of oxygen gas. We know we've got 3.4 grams of A. So the starting point is to think about how much work we need to do. So we have the data provided and some workings that we need to include. We put our equation in that we've worked out in part B, and we can use the technique DMEMA, or data moles equation, moles answer. So 3.4 grams of sodium nitrate, or technically sodium nitrate 5 you could call it, using oxidation numbers and Roman numerals. Working out the moles is 3.4 over 85, giving you 0.04 moles. And therefore, using the equation where you've got a mole ratio of 2 to 1 between the sodium nitrate and the oxygen, that means you multiply 0.04 by a half to get 0.02 moles rather of oxygen. And at room temperature and pressure, so looking here, at room temperature and pressure for any gas, the volume in decimeters cubed is 24N, so therefore it's 24.0.08 equals 0.48 decimeters cubed. Or you could say 480 centimeters cubed using V equals 24,000 N. Okay, so hopefully this has been a useful roundup of how this type of question might be approached. Thank you for your time, as always, and until next time, see you soon.